So we're going to talk first about the viewing transform. So because there's several transforms, I'm going to show this picture and then try to walk through this way. So far, everything we did is in world coordinates. So we had a bunch of cubes and we used modeling transforms to move them around, but we landed those cubes in some location in our world. And so far, our world exists from -1 to 1. Right, in both from left to right, top to bottom, and also back to front. Some of you have encountered clipping planes. So when you move your object too far backwards or too far forwards, they don't exist in your world. Your world is a very small world right now, and all your objects live in it. So the viewing transform is going to let us set up a camera to look at our world from different views, and that's what we're going to talk about first. And there's going to be some more stages. This projection is going to handle perspective. We're not going to talk about that while we're doing viewing. And then there's going to be some screen and clipping and other things, and we'll talk about those later. So here's the conceptual idea. We have some camera in our world. It's looking at our 3D world, and we'd like to get the projection on the screen or in our window. And we'd like to know what's going on. How do we set up our world to be viewed from a camera that can move around in different locations? So here's the top level idea. And I think that this is a not very intuitive way to say things, but this is what's happening when we do viewing. Your camera exists someplace in world coordinates. And we'll later talk about how do we specify that. And it's looking at our objects. The viewing transform is going to be a matrix that rewrites all of the coordinates of our object in a new coordinate system. So instead of the world coordinate system, we're going to move to the view coordinate system, also sometimes called I space or I coordinates. And what is this space? This is the space where the camera has been moved onto the origin and is looking down the -z axis. So whatever we have to do to get this camera to move onto the origin looking down -z, that's going to be what's going to be the matrix as the viewing transform. And of course, the world is going to have to change also, together with the camera changing. There's going to be a rotation. So what does this look like? Right, we're going to call some command. There's going to be a look at command. It's going to make a matrix. That matrix is going to make this transformation. Okay, so here's a little animated GIF, which I hope is coming through. Can somebody confirm in the chat window for me? And the idea is we want to get our camera on the origin, looking down -z. So here's our camera. And when we apply our transform, the camera moves, but the whole world moves, right? So the thing that the camera is seeing isn't changing, right? We're just doing a coordinate system transformation. So why is this important? Because later transformations that we're going to apply, in particular the projection transform, assumes that the camera is in this location. So we want to get it set up in this way. So here's the command. GL look at. The first thing we specify is the I location. So this is where the camera is at, and it's XYZ. So it's our camera position is at I. We're going to specify a center or an at. So here it's labeled at, here it's labeled center. This is the point where we're looking at. This is a point. This is a point. So there's a vector here of the direction we're looking, but the thing that we specify is the at point. And there's an additional value that we need, which is an up value, which tells us which way is this camera spun, clockwise or counterclockwise, around this vector between these two things. And we'll look at an example. But the idea is in your code, you're going to call this command and get a matrix, which is going to do the transformation we want to do. In old OpenGL, there was something called the model view matrix. And so when we made this call, it set the model view matrix. There's another matrix that was called the projection matrix. And when we set up perspective, which is going to set projection, it set that matrix. So we're talking about this matrix right now. And we'll talk about this model view versus just view in a little bit. What does it actually set? Okay, here's the matrix that it actually sets. I think you don't need to know it. But the idea is that we're going to do this M matrix here as a rotation. So by specifying a coordinate frame, we can do a basis transformation from this space into the coordinate space oriented down -z, and this turns into a rotation matrix that does that. And then the next thing we need to do is we need to get our I on the origin. So since these run right multiplied, we're putting it on the origin first, and then we're doing the rotation. So this is the sequence of commands, essentially, of what's going on inside of here. But you won't have to do it this way. You're going to be able to do it with the look at command. So what do these commands do? Okay, so I've made some little animated GIFs so that I think it makes it very intuitive what's happening with this command. So ignore perspective for right now. We're dealing with look at. So here I am changing the Y value of the I. And so what do we see? We see our camera is moving. The I position is moving up and down, but since the at position is not moving, right, that's the center, is staying on the origin, our camera is tilting around looking at this point. Okay, this is one control we have, and we have XYZ control of where is our camera looking. We can also change the at point. So here I am, I'm changing the Y coordinate of the center or the at. And here it is, this point is moving up and down. So we can change where are we looking. And on the right, we can see what's going on in our frame when we make this change. And here's what the up is. People find the up not very intuitive. So I'm changing one of the coordinates of up. And what that's doing is it's changing the coordinate system as the direction vector that we're looking stays the same, but the rotation around this vector changes. Now, in general in 3D graphics, you may have to worry about this. For your world, you're probably just going to set this to Y equals 1 or Z equals 1, depends on which way you've got your world oriented. If you're in your default space, probably Y equals 1, and just leave it there. You never have to change it. You don't need to enforce that the up vector is orthogonal to the other vectors. Intuitively, it would make sense if the up vector was orthogonal to the direction vector, but that's not actually required. GL will take care of that for you. So if you're not moving around completely crazy, you can just keep it, towards the sky in your world and leave it set. I have some slides here because some of you will watch this, either not watch my video and just go back and reference the slides. You won't be able to see the animated GIFs. So I have some examples of what happens when we change I and up. I'm going to skip over those since we just saw animated examples, which I think are much more clear. The tools that I used to generate those GIFs to stick into the slides, I grabbed from these websites. They're nice interactive tools if you want to go play around with it. So there's one point that I want to make here about what's going on with this view matrix, right? I told you there used to be a model view matrix. So the view matrix and the model matrix, they do a similar thing on the screen. And indeed, we used to have something called the model view matrix. It was just the modeling matrix times the view matrix. So you've been generating these model matrices previously. It's how you were animating your blocky creature. This view matrix is what's new that we're talking about today. So why were they previously combined? So let me go to this next animated GIF. So here I'm doing a modeling transform. In the beginning, we have to wait for it to come back around again. But in the beginning, we have our camera sitting on the origin. The teapot's around it. So I have to move the teapot away so that I can see it. Here it comes. Okay, so now we're going to move the teapot away. Now I can see the teapot in my view. Okay, I can get the same effect of seeing the teapot by backing the camera off and moving the camera backwards. And similarly for rotation, I could rotate the teapot or I could rotate the camera. And in these two cases, right, so here's teapot going away. Okay, here's teapot going away again. One was modeling, one was viewing. Here's rotating teapot. There's going to be rotating teapot again, but this time happening by changing the camera, right? So there's somehow a duality between the camera and the model. They do the same things. And if we look inside the matrices, what I think is nice about this demo is we have this matrix view. The combined thing that's going to happen to our points of the modeling and the viewing, we can see that something similar happens. When I start out, my model view matrix is just identity, right? And then when I push the teapot away, I get a translation in my model matrix, and that shows up in my total multiply. And then later, if I didn't do the modeling, but I instead moved my camera, I end up with the same multiplied thing out in the end. So this duality between the modeling and the viewing is the reason that in old OpenGL, there was a single thing called a model view matrix. And your book uses this in some places also too, which is why I thought it's useful to suggest this. Now for your code, I do not suggest that you pre-multiply these and pass a model view matrix into the GLSL vertex shader. I suggest that you keep these two concepts separate because I think it will be more clear. The viewing matrix is about the camera. The only way you ever set the viewing matrix is you use the look at command. The modeling matrix, these are the ones you've been doing, and they place your objects into the world coordinate system, the same way you've been placing objects all along. And you pass these two things separately. I think your code will be cleaner and easier to understand if you do it this way.